Thanks for joining us tonight for our latest Society Talk. Just a reminder, next Tuesday, the 22nd of September, 8 p.m, we have our AGM, which is all online. Please join. We really need you to be on board for this one. The observatory is taking another step to be reopened on Saturday just gone. So it's a bit of a long process, but we need to make it safe for when we do open, to have blended meetings, everyone can enjoy it and be as safe as possible. Thank you. The reason we're here tonight. Tonight's speaker has a long association with astronomy, beginning with a casual look through a telescope to joining Guildford Astronomical Society to help others on their astro journey, also renewing his own astronomy vows. An author and co-author of many scientific journals, also delivering well-received lectures and public outreach programs. Our speaker tonight spent time at the Max Planck Institute in Germany, developing prototype software for the ExoSat and ROSAT spacecraft that delivered many discoveries. These spacecraft were the forerunners of today's X-ray space telescopes. He is president of the Federation of Astronomical Societies, also vice president of the Royal Astronomical Society. We live in a unique time of planet-wide connectivity, but at what price? So here for you tonight to explain why it's not a good idea to fly the Panamanian flag in space, please welcome Dr. Paul Daniels.
Okay, thank you very much. I'll start by putting up the title slide. Let's just switch over to my... Okay, so the talk tonight is going to be about the Megaconstellation Threat. And my apologies to all of you who were ready to hear my talk about 3 weeks ago, but unfortunately I fell ill right at the last moment. So I'm so glad that I was able to come back and talk to you tonight. So the Megaconstellation Threat. So first of all, what are megaconstellations? Then I'm going to talk about the threat to the different sorts of astronomy, and it has implications for the safe and sustainable use of space and being able to get access to space at all. There are some legal challenges that may oppose the rise of megaconstellations, and I also have some concerns about both some of the legal issues and international legal issues, and also international tensions that could be raised by the rapid growth in these megaconstellations. So the satellite era started back in 1957, and it's a sobering thought, I think, for many of us, and I was born in 1955. It's a sobering thought that satellites have grown in number within, for many of us, our lifetimes. There have been about 8,000 launches of satellites since then, with something like almost 2,000 of them still active at the moment. Back in the early days, the cost of launching a satellite was very high. A 6,000 to 8,000 kilogram satellite was about 100 to 400 million. So that was very much in the cost range that only governments and large corporations could afford. Over time, the cost of launching has come down. The electronics has become smaller so that the satellites themselves can be made smaller. It has the option now of being able to ride share by putting multiple satellites into the same launcher. And so in general, the ability to launch many satellites as a network has come about. One of the early small satellites was the CubeSat, and a small CubeSat, which is about 30 centimeters by 30 centimeters, sorry, less than that actually, small CubeSat would cost about $20,000 and a relatively small cost for launching it. So as you can see, the problem is, in some senses, that the low cost of satellites means that it's easy to launch lots of them. So Moving on. First of all, talk a little about the different types of orbit. We have the high Earth orbit. There aren't many satellites in that. This is outside the geosynchronous orbit altitude. When I mean altitude here, I mean distance above the Earth's surface rather than distance from the Earth's center. Then we have the geosynchronous and geostationary orbits. The difference between them is that geostationary is inclined at 0 degrees to the equator, coplanar with the equator, and that means that those satellites always stay at a fixed point in the sky. The orbital period is the same as the rotation period of the Earth. So ideally, if you wish to have a fixed satellite dish, you have to have your satellite in a geostationary orbit. The other kind of orbit that rotates at the same rate as the Earth is the geosynchronous orbit, where the orbit is inclined to the equator, which means that the satellite moves above and below the equator, always staying roughly over the same longitude. If the orbit is slightly elliptic, then it means that sometimes the satellite will move in advance of the Earth's rotation rate and sometimes behind it. So it will actually then proscribe, if you like, a figure of 8, an extended figure of 8 on the surface of the Earth. So that's the geosynchronous orbits, synchronous with the Earth, but not necessarily stationary in the sky. So clearly you'd need a satellite dish that can track the satellites for that. Then you have the medium Earth orbits. Now, there aren't so many of these. They're not as useful. Where they tend to be used maybe is for surveillance satellites. One particular version here is the Molniya orbit, which has a specific altitude of, semi-major axis of 20,200 kilometers, which gives it a 12-hour orbital period. And if you incline that orbit at 63.5 degrees, the Earth's bulge doesn't cause the orbit to precess. So it has the advantage of passing over the same place on the Earth's surface once a day, and another place also once a day. But because of the high eccentricity of the orbit, it means that certain places on the Earth's surface can be gazed at for a long period of time before the satellite then dives in round perigee and then nips back out again to apogee, where it can again look at another point on the Earth's surface. So the Molniya orbit is a very useful one for the military who want to put up spy satellites and so on. Then the other ones, which is mostly the subject of tonight's talk, is the low Earth orbits or the near Earth orbits. Low Earth orbit seems to be the preferred abbreviation. And also VLEO for very low Earth orbit. So low Earth orbit, less than 2,000 kilometers altitude, and currently, well, that number is probably not correct now. Currently, it's probably nearer 2,000 in satellites in low Earth orbit. Very low Earth orbit tends to be those that are only a few hundred kilometers up, so 500 kilometers or something like that would count as a very low Earth orbit. Okay. So megaconstellations. First of all, what is a constellation? Well, a lot of these satellites, given that they are now so cheap and you can put so many of them in orbit, they work in concert. They work as a system of satellites potentially communicating with each other. So that, for example, the American GPS satellite system could be classed as a constellation. For megaconstellation, you're probably talking about more than a few hundred. So this table here shows the satellites that are currently known about. However, it's a little out of date. It's always changing. If you look at the various filings going into the US FCC, the Federation Communications Commission, they always updating what orbits they're going to use, and In fact, this table is a little different to the one in my FAS newsletter article, because shortly before my article came out, and I didn't spot it, SpaceX decided they were going to change the orbits of the satellites that were further out at 1,200 kilometers and bring them down to more in the 500, 550 kilometer range. So things are always on the move. And in fact, also on this table here, it shows the OneWeb satellites. And in fact, OneWeb, I've heard recently, are planning to launch some 1,200 of them into an 8,500 kilometer orbit, which is a serious no-no from the point of view of astronomy, but I'll come on to that later. So what does this look like in terms of this many satellites in orbit? I'm looking here at just the SpaceX ones for the moment. So I'm going to just switch over my presentation, if I can work out how to do this. So I'll stop presenting that and go to this one. So what you should be seeing is a picture of the Earth as a globe hanging in space. Ignore the starry background. I haven't been able to get that to work properly yet, but this is an application I wrote. Incidentally, I'll give the link to it later, but this is on the web and you can go and play with this to your heart's content later as well. But this is the view of the Earth as seen from a geostationary orbit. And you can see it's an Earth that is pristine with no satellites. If I zoom in, the frame rate's a little lower than when I'm not presenting it. And if I turn on the 12,000 satellites that they expect to launch in the initial batch, this is what they look like. So you can see that's a pretty disastrous coverage of the Earth's surface. In my paper, I referred to phase 1s, 2 and 3 of the launches. This is all of the ones that come under phase 1 and 2. The phase 3 ones will look like that. So you can see the reason for having a talk like this one. Okay, I'll come back to these later on. I'll just turn them off and stop the animation. But you can see that here there's a pretty good reason for concern about what's going to happen. So there are thousands here now. In this number of 58,000 or so at the bottom of the table, I haven't included here any of the OneWeb satellites. They have ambitions to launch over 48,000 of them. The satellites that you just saw for SpaceX are about 42,000, and that's not counting the ones from Amazon or the ones from Facebook. There are rumors that Facebook is planning to launch a large constellation as well. So we could be looking at something like 4 or 5 times the ones you've just seen. All of them in low Earth orbit or very low Earth orbit. Okay, so looking in more details at the Starlink project, I have here the table showing my phase 1, phase 2 and phase 3. When SpaceX made an application to the FCC to be able to launch these satellites, they were given permission for the phase 1s and the phase 2s. This is for the first 12,000. That was the white satellites in my animation. It was the first time such a large number had been applied for, and so the FCC decided that it was unreasonable to impose the usual constraints on when they had to have them all up and working by. And so they have to have at least half of them up by March 2024. So that's 6,000 by end of March 2024, and then all 12,000 of them by the end of March 2027. At the moment, they haven't been given permission for the phase 3 satellites. So, sorry, November 2027. They haven't been given permission for the phase 3 satellites. So clearly, the big hope is that they won't get permission to launch the other 30,000. And hopefully also, if they are stopped in their tracks at launching the 30,000, other companies such as OneWeb will also be stopped in their tracks from launching as many. So there's obviously a lot of legal and political discussion going on now to try and, at the very least, slow down or delay SpaceX's progress on this, and similarly there will be discussions going on here with the UK Space Agency and the UK government and so on, so that OneWeb behave in a responsible manner. Okay, you'll see that most of the satellites here in phase 1 are in low Earth orbits between 540 and 570 kilometers with a range of inclinations. But you'll see that if you add up the first 2 rows there, you've got 3,000 of them which will have their inclination at 53 degrees. And I suspect that's chosen so that satellites will cover the North American continent and Europe and parts of Asia. Unfortunately for us, 53 degrees also means that the points where the satellites are traveling their slowest in a latitude sense is over us. So we will see a constant concentration of them above our skies. Okay. So I did some very hairy geometrical calculations to work out where the density of satellites will be. So first of all, looking here at the phase 1 satellites, this is the blue ones, you can see that there is a peak of concentration of satellites in the sky at 53 degrees. What I've effectively done here is I've looked at the proportion of the orbit between, say, 52 and 53 degrees, and then between 53 and 54 degrees. So this is a fairly straightforward bit of trigonometry to work out how much of the arc of the orbit is there, and then assume that all of the satellites in that orbit are smeared out over the orbit, so you can work out roughly what the concentration of satellites will be between any given pair of latitudes. It turns out to be a relatively low number in the terms of 0.2 of a satellite per 100 square degrees, which sounds very low. And just as an indication, the square of Pegasus has an area of just over 200 square degrees, so it's about half of the square of Pegasus for 0.2 or 0.3 of a satellite. This graph is again a little different to the one in my previously published article, because in bringing the 1200 kilometer altitude satellites down to a lower altitude, they're actually spread out more in the sky. Sure, they are going to be brighter, but if you imagine holding a net high above your head, the nodes of that net where the strings tied together is relatively close together, but as you bring the net further down, the spacing of those nodes, angular spacing of those nodes is greater. So the actual density of the nodes of your net in the sky goes down. So it actually caused the phase 1 bars to be lower than in my article, as shown in this graph. You can see that some of the satellites are in the higher altitude orbits, higher inclination orbits, sorry. So that explains why we've got some of these here in the higher latitudes here. This does give some internet coverage over the more northern latitudes in Europe, and that would include places like the Orkneys and parts of Norway and so on. but they won't have the same internet coverage that SpaceX are hoping to get with the satellites in the lower inclination orbits. So, what are the satellites themselves like? The first few that were launched, the version 0.9 satellites, were very much prototypes, and they've now upgraded those. They're slightly more heavy. They've now got the latest ones have a visor on them. One of them was made dark to see if it would be less visible, but it only dimmed the satellite by about 0.8 of a magnitude, so that's not terribly helpful. And despite the fact that the visor sat, where a panel is attached to the satellite to shade the underside from sunlight and so reduce the brightness as seen from the ground, despite the fact that it was meant to be a trial, they seem to have committed to that, and they are now launching all of their satellites with the visor on them. As far as I'm aware, there haven't been enough observations from the astronomical community to say whether or not that is an effective tactic or not. So maybe there are other advantages, maybe in keeping the electronics cool or something like that. But the problem is, what do we do if these mitigation attempts aren't terribly successful? The satellites have Hall effect thrusters using krypton gas. So they have a gas canister of krypton, which is ionized and ejected at high velocity out of the satellite to allow it to do some station keeping. Also, when the satellite comes to the end of its life, they will reserve some of that gas for slowing the satellite down to allow it to deorbit. They all have beam steerable antennae underneath, which means that using a phased array, they can steer the beam. In fact, multiple beams can be steered down to different points on the Earth's surface. It has a single large solar panel, and it has a star tracker navigation system to make sure that the satellite can orient itself correctly. Something else the satellite has in common with a lot of other satellites is something called a magnetotorquer, which is effectively a large coil through which you push a decent amount of current. It's a set of 3 orthogonal coils, so that you can actually rotate the satellite using the Earth's magnetic field to provide the magnetic field that the satellite's coils work against. That will allow it to do some rotations without having to use the krypton gas. And in particular, one of the mitigations that has been put forward by SpaceX was to rotate the satellites continuously so that they can maintain the illumination of the solar panels, but to always present the underside of the satellite to the ground, and so hopefully reduce the amount of reflection off the satellite. Eventually, and I think some of them already have now, they will have inter-satellite laser communications, and that will allow, in principle, an internet signal to be beamed up to one of the satellites. It will then pass through one or more satellites in orbit and then back down to the Earth to a ground station. And because of that, there is the potential for faster communication via Starlink than across a set of relays and optic fiber on the ground, on the basis that the majority of the signal will pass through vacuum in space, whereas on the ground, of course, it has to pass through optic fiber, and the speed of light in glass is lower than that in a vacuum. I think I've seen some figures reported recently by SpaceX for something like a 20 millisecond latency on their internet connection, and that would certainly be better than most other solutions on the ground, unless you happen to live very close to a ground station on the ground. SpaceX have applied for a license for up to 1 million ground stations in the United States. I don't know whether they will ever achieve that. Excuse me. But they're obviously going to require ground stations in other countries as well for this to work. So one of the things you have to concern yourself with, of course, is that they can't collide with each other or with anything else. Having that many in orbit, this is a major task. And it was estimated by Manfred Wittig at MEW Aerospace that 1 kilometer CubeSat traveling at 7 kilometers per second has the equivalent of about 6 kilograms of TNT explosive force if it collides with something else. There are estimates of how many particles and things there are in orbit at the moment, not just satellites, but also space debris, rogue spanners that have gone loose, nuts and bolts that have broken off, and also things like large bodies like boosters that are still in orbit, but small things too, like flecks of paint. And also you may have a satellite that's being impacted by a micrometeoroid, may not have caused significant damage to the satellite, but it may cause small globules of metal to spallate off the surface of the satellite, and therefore you do have also the potential for very small metallic particles in orbit, simply because you've got a large number of bodies up there. They are capable of being impacted by natural bodies as well as potentially by other satellites and by space debris. It's absolutely essential that we work on reducing the amount of orbital debris up there in space. So especially when we're now putting up as many satellites as being proposed by SpaceX and others, you could well see that there could be a lot more debris generated. Not necessarily run away, but there could be a lot more. SpaceX have claimed that their satellites will be autonomously able to avoid other satellites, and they've teamed up with the Joint Space Operations Center, who are tracking other satellites, and they will then upload avoidance details to their satellites to avoid others. That doesn't help, obviously, if one of their satellites goes faulty and can't maneuver anymore. It represents it would then represent effectively a dead threat in low Earth orbit, which is one of the last things you want. The other consideration, of course, is that these satellites contain batteries, and batteries aren't necessarily foolproof. And you may also have electronics that could go wrong. I'm sure we've all heard of equipment where perhaps a resistor has blown up and overheated, or a capacitor has blown up. And also it contains a compressed gas canister of krypton. And so again, it's possible that could explode. You may have perhaps a micrometeoroid impact or a space debris impact on the satellite, and that could cause it to explode. So there is a lot of work to try and shield the sensitive parts of the satellite from impacts, but also from in the explosion generating external debris. I suspect that that's a best hope, and that you can't perfectly guarantee against that. So the other thing is we're going to have all of these satellites up there, and they have a lifetime. So as part of their plan, their plan that goes to the FCC that authorizes the launches in the US, they have to say how they're going to deorbit the satellites afterwards. SpaceX said that for a satellite in a 550-kilometer orbit, if the satellite goes dead, in 5 years' time it will deorbit of its own accord. That does mean, of course, if the satellite is dead, that other satellites will have to get out of its way. By other satellites here, I also include the International Space Station, the Hubble Space Telescope, and other satellites that are in orbit. And some of those are not maneuverable either. So you just have to hope that SpaceX have a reasonable reliability on their satellites and that they don't die in service. So the first aim is to use some of the fuel to lower the perigee. So the orbits of these low Earth orbit satellites are pretty much perfectly circular. At 550 kilometers, there is some atmospheric drag, and some of that krypton gas thruster will be used to overcome the atmospheric drag at those altitudes. But one of the consequences of atmospheric drag acting on a satellite is to circularize the orbit. If you imagine an elliptical orbit, then the drag force will be stronger when the satellite is at perigee than it is at apogee, and slowing the satellite at perigee lowers the apogee altitude. And so that then means that there is a greater degree of symmetry in the drag force, and the orbits will circularize. So back to this, the effect will be to lower the perigee distance, but keeping the apogee at 550 kilometers, or whatever the in-service orbit altitude is. This will take some time because the krypton Hall effect thrusters are very low thrusters, and it takes a long time to raise the satellites from their initial orbit up to their service orbit, and correspondingly a long time for them to deorbit back to the point where the atmosphere has sufficient grab on them to cause them to re-enter completely. They will retain some of the fuel to allow them to do some maneuvering on the way down. The other thing is that the satellites will initially be launched into what SpaceX call an open book, where the solar panels will be parallel to the body of the satellite. The body of the satellite is a very thin panel, flat panel, and the reason for that is that the initial orbit is a very low one at 290 kilometers or something like that, where they check out the electronics before they raise them up. Once they're on their way up, they will then bend the satellite at right angles so that the solar panel faces the sun and the body of the satellite faces the ground. Whether or not, and this is something I have to ask SpaceX, is whether or not in the process of bringing the satellites down again, they're able to flatten the satellites out again, so that they will be able to make use of the added drag of a flat panel face on to the direction of travel to maximize the drag and minimize the time to re-enter. They also, during this time, slow down the reaction wheels through another way of allowing the satellite to rotate, drain batteries, and power the satellite down generally. And the hope is that a proper deorbiting process means that within a few weeks or a few months, the satellites will re-enter the atmosphere and be destroyed. As I say, this doesn't answer what they do if the satellite becomes unresponsive, either because you can't communicate with it or because it's just simply died completely. So the mission lifetime is about 5 to 7 years. If SpaceX do get permission to launch the other 30,000, so that you have 42,000 satellites in orbit, then that means that will be something like 500 to 700 of them per month deorbiting, and 500 to 700 per month needing to be launched to replace them. So this has consequences for pollution from the launch vehicles and re-entry. It's a real waste of the amount of expensive rare earth metals that are often used in electronics, and to have them vaporized in the Earth's atmosphere seems very wasteful. It also means that whereas SpaceX are attempting mitigations to make the satellites appear fainter when they're in service in their orbits 500 or 600 kilometers up, it means that they are going to be brighter on the way up and brighter on the way down. So even if you assumed that only the lower 50% of that transition up or down is bright enough to be seen, that still means about 600 fairly bright satellites in the sky to the naked eye, or in astro imaging. So SpaceX are going to orient the satellite to reduce reflections down to the ground, but it's not obvious, and this is again another question I need to ask them. What are their plans for minimizing reflections when the satellite is deorbiting or orbit raising? Because when they're orbit raising, they want to minimize the drag so that their krypton thruster has the maximum effect. And during deorbiting rather, they want to maximize the drag to minimize the time to re-entry. And they may not be orientations of the satellite that are optimal for also reducing the reflections. So there are some questions there to go to SpaceX. So as well as the satellites themselves being visible as they transit, there will also be 600 satellites per month re-entering the Earth's atmosphere. So it's about 20 per day. And they will cause, somewhere around the Earth, they will cause a bright streak across the sky as they re-enter. So it may be that you're the unfortunate one that has your 1 hour exposure ruined by a re-entering satellite. So the next thing is this thing, the Kessler Syndrome. Donald Kessler, 1978, and Burton Coeur-Palais published a paper based on some work that Kessler had done on asteroid collisions in the asteroid belt, and he sort of carried the theory over to satellites in Earth orbit, and concluded that if you had too many satellites in Earth orbit, there was potential for a chain reaction of collisions and space debris, and the space debris causing further collisions and so on, so that you ended up with a fog of small space debris around the Earth that ultimately would turn into a ring system around the Earth. Now, this is likely to be less of a problem with the low Earth orbit satellites, because the effect of drag on a body is greatest for low mass, large surface area particles. And it turns out that the smaller you make a particle, the more effective the drag is on it. So if you did have debris in low Earth orbit caused by a collision, then you would eventually find that debris re-entering the Earth's atmosphere. I've spoken to Hugh Lewis at Southampton University. He's on the same RAS Megaconstellation panel that I am, where we discuss these sorts of things. He feels it's not a problem because the debris will re-enter fairly quickly. My concern is that if you had a sudden spike in debris, you could have a period of time where getting to Earth orbit would be dangerous. Being in Earth orbit, and I'm thinking here of the ISS and HST, being in orbit could be dangerous, and you may cause a lot of damage, even if that spike in debris would eventually subside over a year or so. And it could be that that spike in debris could cause another collision or more debris, and even if it's not a self-perpetuating Kessler Syndrome type of runaway, you may get a spike in debris that persists for a significant amount of time, making the access to space and the use of space quite dangerous. And not only is there the issue of the damage that Starlink satellites may cause to other Starlink satellites, but there's the damage they may cause to other satellites. And I can imagine the legal issues of a Starlink satellite that has collided with another one. Who pays for it? More to that later. So the next issue is on the radio side of it. There are, first of all, the radio bands allocated to SpaceX for communicating upwards with the satellite, and the radio bands that the satellites will use communicating back down to Earth. So these are the principal bands that have been allocated so far. I have to admit here that radio astronomy is not my forte. So I know that in one particular case, I think in particular for the ones here on the left, the bands are very close together between the radio astronomy and the downlink from the SpaceX satellite. They have agreed to leave a gap between their downlink band and the protected radio astronomy bands. Certain bands are protected and no one should be able to use them, but with the best will in the world, radio transmitters can produce sidebands, and though you want to reduce sidebands so that more of your energy goes into your primary communication band, sidebands may cause some interference in the radio astronomy band, especially given that radio astronomy equipment is designed to be so sensitive. Also, you have other problems in that some of the radio astronomy bands are not protected. It would be greedy to protect all of the bands that we want, and especially given that you may have a particular molecular band due to water or something like that. But if the source of that particular band is redshifted, it may mean that the band where that particular emission line has shifted to a different frequency. So radio astronomy has a big problem, not only with the crowding of the spectrum, but the fact that the things they want to look at aren't necessarily emitting at the band that they would if they were stationary relative to the Earth. The other thing is that SpaceX have said that because the beams from their satellites are steerable, there are certain places on the Earth's surface that are radio quiet zones, such as, for example, around the new ALMA radio telescopes and so on, and the square kilometre array, where you have on the ground, they have a radio quiet zone where nobody's allowed to use a walkie-talkie or any other kind of transmitter within a certain distance of the installation. And so SpaceX has said, well, they will ensure that their satellites are programmed to steer the beams around these radio quiet zones. So this is all well and good if you are a high-profile radio astronomy observatory, but some of the smaller radio astronomy observatories that don't have an RQZ status may find it harder to get SpaceX to steer the beams around them. And that's before you even think about the amateur radio astronomers who probably won't have a say at all in where SpaceX's beams are steered, especially if your radio astronomy setup is in your back garden in the middle of Manchester. I can't see SpaceX saying, we're not going to beam to Manchester because you've got your radio astronomy setup in your back garden. The other problem is that radio astronomy satellites receivers are so sensitive that the satellites are broadcasting, even if they turned off their broadcasts, the electronic noise from the satellites is just about on the limit of detectability by the larger satellite arrays. So even if the satellites weren't broadcasting intentionally, even if they steer their beams away from radio quiet zones, the electronic noise of the satellites is also just about detectable. But that's potentially predictable and maybe can be removed from the data with careful processing. This isn't a new problem for radio astronomy because they've had to contend with other satellites for years anyway, but this will make the problem so much harder. And to my mind, the radio astronomers are going to feel the brunt of this more than the optical astronomers. So a little bit about the geometry here. We've got in the upper diagram, we have to scale a 1,000 kilometer altitude satellite. The initial modeling that was done assumed that people wouldn't want to observe much below 30 degrees above the horizon anyway. In the direction of sunset, it'll be twilight anyway, and in the opposite direction, you've probably got too much air mass anyway, and dimming and other problems to make observations there reliable. Having said that, some people do observe and image at those altitudes, and if you're, for example, trying to find objects close to the sun in the sky, you may be observing below 30 degrees. But you can see from the geometry of this first one that you have satellites here at the top that are where you've got the satellites up here that are visible because they're still in the illumination from the sun. But you've got down here the glinting satellites that are also illuminated by the sun, but in particular down at those angles you may have problems with specular reflection of the satellite, not just the satellite being illuminated. And this is particularly one of the things that SpaceX are trying to avoid in the orientation of the satellite. But I suspect that that's going to be a very difficult thing to achieve down close to the sun in the sky. So when the sun is lower down, you've got a much smaller area here of satellites being illuminated by sunlight, and you've still got glinting satellites visible here, but potentially they are still going to be a problem. When the sun gets below a certain elevation, below the horizon, many of those satellites, if not all of them, will be in the dark, in the Earth's shadow, and so all of the modelling has to take into account what the season is and what the time of night is, and it turns out that the season will have a big influence on this. Okay, so you're probably all aware of this, so I'll be very quick with this one. You can see that this is a calculation done for Birmingham at 52.5 degrees north, and it shows that in mid-summer the sun is only 14.1 degrees below the northern horizon, and in midwinter it is 60.9 degrees below the northern horizon. So that has big implications if you're looking for satellites north of above the northern horizon, because satellites there will still be very much illuminated in the summer and not in the winter. And of course, in the summertime, you've got illumination much more around to the east and the west as well. So this graph, it's a reworking of one published by Oliver Hainault, who works for the ESA, and it shows for the elevation of the sun, it shows what percentage of satellites are likely to be illuminated. So you can see that for the low Earth orbit satellites at 290, 340 kilometers, these are the ones for the phase 3 that are being launched, but you've got 550 kilometers here for most of the phase 1s and 2s. You can see that when the sun is even by the time you get to the to astronomical, the end of astronomical twilight, still most of the satellites at 550 kilometers will be visible. As the sun gets further down below the horizon, so as you get down sort of autumn, winter and spring, you can see that perhaps only 50% of them will be illuminated. So that gives you an idea to calculate how many of those satellites will be visible above the horizon, depending on the time of year. Okay, so if you're trying to work out what's visible, you've obviously got to consider the geometry of the orbit versus the Earth. You've got to consider the Earth's shadow, but you also have to look at the satellite itself. This is a very difficult thing to do, because if you were just modeling the satellites as a diffuse ball of grey, which is what was initially done, your problem's a little bit easy, and certainly some of the initial work that Oliver Haynott did at ESO was on that basis. But very quickly it became obvious that specular reflections off the satellite made this much harder to do. So the satellites are multifaceted. They have different brightnesses and reflections on different parts of the satellite. It depends on the sun satellite observer angle as to how much glinting you get. And it's expected that at 550 kilometers, that the satellites would be between 4.2 and 5.9 magnitudes. So 5.9 magnitudes is right at the limit of most people's naked eye observation in a reasonably dark sky. However, they are brighter than that during orbit raising, and they will be brighter than that during orbit descent. So that's what I say when I'm saying you'll see perhaps when the 42,000 satellites are up there, there will be some 600 or so satellites that will be brighter than magnitude 4.2. I've already said that the dark sat coating didn't work. They painted the satellite black on one of the on the underside. One of the other problems it caused them is that when the satellite has a dark face to it, the temperature of the satellite goes up, and at some point it makes the electronics unreliable. So they abandoned it for temperature control reasons, as much as the fact that 0.8 of a magnitude wasn't much of a win. I've already mentioned the visor that they're going to use, and also the use of the magneto-torquer to help rotate the satellite. So this is from the point of view of the astrophotography. I produced this table in my article. I've taken out the high altitude orbits that SpaceX were originally going to use. As a rule of thumb, you can get the density of satellites in the sky, from my earlier graph. That should be that one. You can use that one. Remember, of course, that this is the number of satellites per 100 square degrees. And the field of view is the field of view of your instrument, be it binoculars or wide-angle camera or whatever. The time of your exposure in seconds. And then here, this is the angular velocity of the satellite across the sky in minutes per second. So by dividing it by 60, you get it in degrees per second. So taking a typical value down here of 0.25 from my graph, that's 0.25, actually that should say 0.25 per 100 square degrees, and 10-minute exposure, and 30 arc minutes per second from this table up here, using a typical value from the middle of this table. You come up for different instruments with this value of n. I actually have used the correct value for this as 0.25 per 100 square degrees, so it's just this description that's wrong. So you can see that in a pair of binoculars, if you were to fix an 8-degree field of view pair of binoculars at one point in the sky, then over a 10-minute period you would expect to see something like 6 satellites passing through your field of view. If you had a typical amateur telescope, then over a period of 10 minutes you might expect to see a satellite appear there 3 times out of every 4 10-minute viewings or 10-minute images. The big problem is down here for the Vera Rubin telescope, which is a wide-angle telescope that is taking 15-second exposures, and even with 15-second exposures, they are going to be a problem for the Vera Rubin telescope. They will have something like 1 satellite for every 6 exposures, which is going to be a real problem for them, because you build a very big, expensive telescope that relies on taking regular snapshots of the sky so that you can do a survey and you can compare yesterday's imaging with the image again in a few days' time. And if you're having to throw away 1 in 4, 1 in 5, or 1 in 6 of your satellite, your images, then it rather puts a hole in the coverage that you would hope to maintain. So this is the link to the simulation I showed you earlier. What I'll do is I'll switch over to this now and run through it with you. Okay, so everyone said okay. So what we've got here is the Earth. I've zoomed into a lower altitude of 13,000 odd kilometers, and the application it's actually written using 3JS as my library. It uses WebGL. Most modern browsers will be able to show this. So if you go back to that link, and I'll go back to that, you should be able to play with this yourself. I am updating it even now, so I can zoom in and fly over different parts of the Earth's surface. And if I turn on the 12,000 satellites, the reason why the satellites look so big is that I need to develop a way, I think, of having the satellites keep a constant size no matter how far away you are from them, or something like that. So there's a slider up here where I can actually reduce them and make them look less obvious. So you can see that this is taken from 1,700 kilometers up. If I go further around, further in, you can see here this line. This is the line because this is the highest point in the 53-degree inclination orbits. So that's why you see what looks like a concentration at this sort of altitude. It's more obvious, in fact, even with the phase 3 satellites, which I'll show in a minute. And you can see that, in fact, you can see over on the side here, we're looking through that ring from the side. And you can see that this is a significant number of satellites to be passing overhead. And it's not just affecting us, it's affecting everyone in the world, unless you live in Svalbard or something like that. So I've also added in things like you can reduce the field of view of your camera. That allows me ultimately to put the camera in the HST orbit and see what a 1 degree field of view from the HST will look like. So as I say, it's still very much a work in progress. Feel free to go and play with that. So one of the things I need to do is improve the frame rate, and I've already got some good ideas on that. You can also see that some of the satellites down here are in the Earth's shadow, and I can turn the shadow on and off. I can also turn the Earth off, so you can see here what the shell of satellites looks like without the Earth in the middle. That gives you a true picture of how many there actually are. That's just the 12,000. If I add in the 30,000 as well, then that's a lot of satellites in orbit. Okay, I'll switch back to the presentation again. So if you want to make a note of that link, I need to improve the performance. The Starry Background is a fixed canvas in the background, so even if you move around the Earth, all the canvas stays in the same place. I'm going to have to work on that one. I want to add in the Amazon satellites and the OneWeb satellites and others as well, and add some other controls. I want to, for example, be able to tie the camera onto the Earth's surface so that you can rotate the camera and look upwards and get a feel for what it looks like. So various other things going on there. So who's affected? Well, this is the professional astronomers, the Vera Rubin telescope. They've done some work already. This is a satellite trail. They use very sensitive CCD sensors, and the problem with CCDs is that they are very sensitive, and if you saturate part of the trail, it means that you also produce artifacts in other parts of the image. So not only do you need to remove the satellite trail, but you can see here that these parallel tracks are artifacts from this saturated trail here. If the trail is not saturated, then you may have the ability to remove the tracking software. But the fact that this is so saturated with blooming either side of it here, where there's some glow either side, means that it's a very difficult thing to remove. And they've concluded that if SpaceX can bring the satellite brightness down to at least less than 8th magnitude when they're in service, but better lower than 9th magnitude in service, then that would give them images that they may be able to, where they may be able to remove the trails. But as has been commented, the trails are still there in the data, and it seems wholly unfair that astronomers should have to work so hard to remove these man-made defects from their images. So the other one is the HST. This shows the Earth down here with this band of orbits at 540, 50, 60, and 570 kilometers above the Earth's surface. So here we see the 4 orbits. The dotted lines bound the upper and lower range of the Hubble Space Telescope. So you can see that the Hubble Space Telescope is very close to the 540 kilometer band. Potentially that's an existential threat for the HST, but not just the possibility of collision with a satellite. If there is a problem in that orbit and there is debris in that orbit, then there's damage potentially from the debris in that orbit. And also, if you're pointing the Hubble Space Telescope away from the sun, you're going to have satellites that are receding away from the telescope, passing potentially through its field of view, and already they are reporting that many of the HST images are being polluted by these satellites passing through their field of view. There was already a problem before Starlink was launched. Starlink will make it significantly worse. Professor Martin Barstow is chairing this RES Megaconstellation panel, and he said that the hope is that there's another 5 years of life in the HST yet, and it could be that the Starlink satellites will make the HST useless before that. HST is not the only one, however. ESA have the Cheops satellite, which is in a sun synchronous orbit, and that will look away from the sun, directly away from the sun, or 60 degrees or so either side of it. And it turns out that some of that 60-degree cone either side will encompass the edge of the higher orbits, so that will have interference from the satellites. And the WISE satellite from NASA is at 525 kilometers in a near-polar orbit, and it may well have its observations damaged as well. And I'm sure there are many others as well that may be affected by this. So the satellites, for radio and infrared astronomers, the satellites don't have to be illuminated to cause a problem. For the optical astronomers, if they're not illuminated, they're less of a problem, unless a silhouette transiting across a body causes a problem, maybe in a solar observation or a lunar observation. But generally, it's the illuminated ones that are the problem. For radio and infrared, that's not the case. They will have emissions of their own. The satellites also emit their own interference from the electronics. Beam steering may not be enough for all of the observatories, and as I said earlier, not all of the bands are protected, and redshift can cause problems. For the infrared astronomers and the sub-millimeter astronomers, satellites that warm up when they are illuminated will retain some of that heat, and so they may well be glowing in the infrared even when they're no longer directly illuminated by sunlight. Just check how I'm doing for time. Okay, I'm running over a little. So we have amateurs generally less affected. The equipment is not as sensitive, and typically amateurs use CMOS sensors with off-the-shelf cameras. So CMOS sensors can more easily, they're not subject to the same artifact problems that CCDs are. Some well-off amateurs use a CCD sensor, and they have the same problems that the professionals will have. There may be the possibility of software apps to make it easier to predict where you can take a picture without it being harmed by a satellite. There is also the possibility for either software or hardware so that you can either disable your sensor temporarily or have a shutter that comes into place automatically connected with the prediction software, so that you will get gaps in your observing designed to deliberately shut out the satellite. Not ideal if you need a continuous observation. And as I said earlier, beam steering isn't going to be a solution for amateur radio observatories. There is a perception problem here amongst the public. It is still being reported. Starlink is still being reported as something of a celestial spectacle. And I groan every time I see the local Norwich newspaper say, "Oh, another 20 satellites coming over tonight from Starlink." For the public, for many of the public, the satellites are a curiosity. But I'm starting to see more articles becoming aware of what this will mean for the nature of our night skies. There was an article, I think, a couple of days ago in The Guardian, which certainly covered what this would be like. Even if the satellites are mitigated in service to be below naked eye brightness, as the professionals certainly hope, there will still be a large number of them visible as they rise to orbit and deorbit afterwards. And it's a real problem, because space and astronomy are huge inspirations for young people, and I don't think any of us can forget the look on a youngster's face when they first look through a telescope at outreach and see the rings of Saturn and stars and so on. And if the sky loses that wonderment because it's polluted by all these hundreds of fireflies flying around the sky, it may mean that they're less turned on to space and astronomy. Maybe the inspiration won't be as great, and maybe that could harm the rate at which some of them go on to become scientists in the future. So what's the legal challenges? And I've got only 4 more slides to go, 3 including this one. So legally, what are the issues? There are always 2 sides to a story. I mean, we as astronomers clearly hate the thought of our skies being polluted in this manner. But on the other hand, there are a lot of people around the world, particularly in rural locations, and a lot of people in rural US who have appalling internet coverage, if any at all. it's bad enough they don't have perhaps their cell phone coverage that they want over there, but they don't get coverage any other way either. So for them, Starlink will be a real boom. So where does the law stand on this? Well, the main one is the Outer Space Treaty of 1967, which has 63 signatories to it, including all the major players. And the US is a signatory to this, or at least Trump hasn't pulled out of this one yet. And that has a number of major things to it, including one which is that if there is damage caused by something you've launched, then you have to pay for the damage that's caused. So if one of the Starlink satellites damages, for example, an ESA satellite, then Starlink will have to pay for the damage that they caused. And I could see that if there are problems with space debris, especially if there is a spike in space debris that can be traced back to a Megaconstellation satellite, be it Starlink or OneWeb or wherever, that there could be major litigation issues here. And I don't know that the investors in these projects have fully considered what they may be laying themselves open to. There was an attempt by 7 equatorial countries, mostly in Africa, not all of them, to try and claim slots in the geosynchronous orbits over their territory. The Outer Space Treaty deliberately said that no nation can own any part of space or any part of a celestial body. So they were trying to lay claim to certain slots in the geosynchronous orbit. On their basis was that if they weren't able to reserve those slots, they couldn't make any money out of it if they allowed anybody else to use them. And not only that, if they ever came to put their own satellites up, they couldn't put them into a geostationary orbit because they would already have had the slots taken by the bigger players who could afford to do it earlier. So you can see their point, but everybody ignored it. And so it was a Bogota Declaration, but it never became law. The Moon Treaty was an attempt by the United Nations to keep the allocation of orbits and the ownership of bodies under jurisdiction of the United Nations. The thing is, by then, by 1979, the potential for space was already becoming well known, and people were looking at lunar bases and space stations and mining asteroids and all these sorts of things. And so even though the UN tried to put this in place, none of the major signatories would sign up to it, including the US and Russia and the European Space Agency. And so even though the treaty came about, very few of the major players would sign up to it. In 2015, Obama signed an act which basically said that US companies, even though they cannot own an asteroid, they can own resources that they have extracted from an asteroid or the moon or another body. So that means that the US can go and mine parts of the surface of the moon. They can't own that patch of land on the moon, but they can own what they remove from the surface and bring back. I suppose part of their argument there is that why would you bother to invest if you can't own what you extract? Trump signed a similar sort of order in April 2020, saying that as a right, private companies could claim and recover resources in space, which also means that, of course, American satellites in space that became defunct remain American property, and nobody else can claim them under some sort of salvage basis. But what was also worrying about this was in his order was, he said, outer space is a legally and physically unique domain of human activity, and the United States does not view it as a global commons. In other words, he's effectively putting in place a land grab ethos. The first to get there and use orbits effectively dominates it and uses it, and nobody else can say otherwise. And that's a very worrying approach, particularly as you'll see in my next couple of slides. In terms of legal challenges, one of the first ones that came about is that there is in the United States the National Environmental Protection Act. All US agencies, government agencies, with a few exceptions, have to abide to NEPA, meaning that every act that they pass, every license that they give out to do something, has to have a full environmental impact assessment. That can obviously raise the cost of any projects, and it can also delay projects. Unfortunately, the US FCC isn't bound by NEPA at the moment, and 2 US senators are challenging that. It may be that if they change that so that the FCC becomes liable to have to observe NEPA and have to do an environmental impact assessment on every satellite that is launched, then that could delay further Starlink launches, but it wouldn't necessarily mean that they have to take down the ones they put up there. There is another possibility, which is that the FCC is required to continually update its policies. This is the US Council on Environmental Quality. This hasn't been done for the last 30 years, and so the FCC has technically broken the law, and so maybe you could get certain of the licenses that they've issued nullified on the basis that the FCC wasn't legally able to issue them because they are pursuing consideration against environmental issues. I don't expect either of those to carry much force. So the last couple of slides. SpaceX are already getting military contracts to explore the use of Starlink. For example, the use of Starlink satellites to communicate with cruise missiles to help guide them to their targets. The use of Starlink to communicate with a refueling plane and a refueler plane, a refueling plane, to allow a more closer, a more accurate alignment of the aircraft for refueling purposes. Also, things like to give them communications coverage in polar regions. There are all sorts of reasons why the US military would like to be able to use something like Starlink, and of course, giving Starlink military approval means that politically they've very much got their foot in the door, and it's going to be much harder to stop Starlink, stop SpaceX getting what they want. As an entrepreneur, Elon Musk is really the US golden boy, and particularly under the current administration, I think he could probably get away with whatever he wanted. Trump signed into existence the US Space Force in December last year, and part of their remit is to protect US and allied interests in space. And so not only can they now, according to Trump, land grab parts of space, but they've also now got a space army to allow them to enforce that land grab. So, for example, if another nation decided to start taking laser pot shots at Starlink satellites to try and degrade the military capability of Starlink, the US would go after the nation that did it. They would consider that an act of war. I'm going to quickly switch over to this Vision for 2020 document, and because that shows that the US have had designs on space for some time. This is a document that was produced a few years ago, and it was one of those, a bit like 1984. There was a time when 1984, and George Orwell's title was Well in the Future. This was the document they produced some time ago, and they were there. They were trying to say, how do we want US use of space to look? I have to say it's a very amateurish looking document. It looks more like something produced by Ming the Merciless than the American military. So you can see the cover here, and the graphics and so on inside, including here this Star Wars type font here. And then going further down, you can see sort of very simple diagrams, the joint vision that they have, including phrases like here, space capabilities, and here, full spectrum dominance, information superiority. Lots of very worrying phrases here. They recognize that their space systems could become targets. And this is all, it's worrying that there are people who are paid to think like this. So control of space. And they are looking literally for, the US is looking for space dominance. And this is the naked proof of it. To protect US national interests and investment across the full spectrum of conflict. So this is a warring nation looking to dominate space for war purposes. Full force integration. This is basically where they're talking about integrating the advantages of space with the Air Force, the Navy, and the land forces. And ending with, towards the end of the document here, what looks like a Star Wars type laser system down to the ground. Somewhat fanciful back then, but it just shows the way that they were thinking. I'll just return to my last slide. No, wrong one. Okay, so you can see here that the US Space Force clearly will have designs on space and occupying space. And in particular, given that space is increasingly being seen as a valuable commercial and scientific resource. And Trump has already thrown down the gauntlet and said, if we get there first, we've got it, it's ours. They can't legally, because of the Outer Space Treaty, they can't own the space that the orbits are in, but they're working on the principle if they get there and they effectively squat on large volumes of space, it makes it difficult, if not impossible, for anyone else to get in there and use it. So the problem is the international treaties are long overdue. The Outer Space Treaty is long overdue. But the problem is that any new treaties will find it very difficult to get the major players to sign up with, especially now that it's become so obvious that space is going to be so important and will be such a commercially useful resource. Why would you want to sign up to anything if you're a major player, if you've already got your foot heavily in the door, where you can mine the moon and mine asteroids and have the technological capability to do it? Why would you sign up to an international treaty that restricts what you can do? And also, what about the regimes like Iran or China or Russia that may not appreciate the fact that flying over their territory are satellites that potentially will allow uncensored internet to get down to their citizens, despite the fact that they've done a lot of work to try and isolate their national internet from the world's internet, so that their citizens aren't exposed to what they consider to be undesirable ideologies. And how are they going to take to having satellites flying over that will allow their citizens with the right equipment to circumvent just that? So you may find retaliatory action taken against the Starlink satellites. And as I've said, that's potentially storing up problems for the future. And finally, just harking back to the last general election, Jeremy Corbyn was talking about nationalising broadband in this country. And I have to say, much as the idea of a consistent, cheap national broadband sounded, it also meant that the UK government potentially, and we can't always assume we're going to have a government as benign as the one that we've got at the moment, note the heavy sarcasm, you may have the potential for a government to be able to censor what we see and control what we do. And exactly the same could apply with the Starlink satellites. We don't know to what extent SpaceX may have to follow an edict from the US government if they were told to turn off the internet over a country that they wanted a trade embargo with. So if, for example, Iran are not playing ball. They say, right, we're going to turn off all of the internet over Iran. That puts the US in a very powerful position that perhaps they shouldn't be. Okay, so that's the end of my talk, and I'm happy to take questions if I can.